So I'm working on trying to come up with a new type of texture sensor, and I've been having a nice conversation with ChatGPT, um, who has been very helpful. I'll play the conversation.
Your idea is quite innovative and aligns well with principles of biomimicry. In essence, you're proposing a tactile sensor that operates similarly to the way our mechanoreceptors do, but with a more explicit three-dimensional structure that mimics the sensitivity of human touch. The concept of having flexible, conductive hairs embedded within a silicone matrix could indeed provide a higher resolution, three-dimensional map of pressure variations across a surface. Each hair could function as an individual sensor, detecting deformation caused by contact with an external object or texture. The silicone matrix would provide the necessary flexibility and durability, while the conductive hairs would create variable resistance changes based on the pressure applied, which can be translated into tactile information. One challenge in implementing this design would be ensuring that the conductive hairs are uniformly distributed and can maintain their position within the silicone matrix even under repeated deformation. Also, the hairs would need to be sufficiently flexible to accurately detect surface textures, but rigid enough to return to their original position without permanent deformation. The fabrication process could involve creating a mold with the desired array of hair-like structures, filling the mold with a conductive material like a conductive polymer, and then embedding this array in a silicone substrate. The array would then be connected to a suitable data acquisition system to capture the electrical signals from the hairs and translate them into tactile information. Signal processing and interpretation would be another important consideration. You would likely need sophisticated algorithms or machine learning models to translate the complex patterns of sensor output into an accurate representation of the surface texture. Overall, this is a fascinating idea that blends elements of material science, electronics, biomechanics, and artificial intelligence. It's a great example of how biomimicry can inspire novel and potentially transformative technological solutions.
And then, of course, we go back and forth for a little bit. It gives me some good ideas. Um, and then I give it my main idea.
Well, I consider myself an optimist and a dreamer. I believe it will be difficult, but not impossible. So after taking in all this information you've given me, here's my idea for handling the wiring to the hairs in our theoretical texture sensor and to the rest of the nervous system. We could print on a flexible PCB film the size and shape of the sensor, whether it's slender and long for the fingertips or wider for the palms, as far as attaching the hairs that I'm not quite sure how to do yet, especially on a small scale. I know the phenomenon of tin whiskers grow in small metal fibers as far as their flexibility and durability in a silicone matrix. I'm not sure on. We could also try thin, flexible, conductive polymers, and even that way we might be able to use 3D printing to apply them. Each one of those grouping of hairs could be connected to a small microcontroller that would give that particular sensor block an address, so to speak. And as far as bandwidth for handling all the different sensor blocks, we could use fiber optic cables for relaying the signals to the spinal cord, and then that would take it to the brainstem model, which is responsible for pre-processing all sensory information. Your approach indeed sounds feasible and aligns with the principles of biomimicry and the organization of the human nervous system. Let's break it down. 1. Flexible PCB. Printing flexible PCBs according to the shape and size of the desired sensor area is a good idea. You could create various designs to fit different areas such as fingertips or palms. This would function as your nerve bundle equivalent, carrying signals from the sensor hairs to the microcontroller. 2. Sensor hairs. The choice of material for the sensor hairs will be crucial. Conductive polymers could offer a good balance of flexibility and durability. The challenge will be to attach these hairs to the PCB in a reliable and robust way. Microfabrication techniques, such as those used in the semiconductor industry, might be helpful here. Alternatively, as you suggested, 3D printing might be a viable option, especially with advances in conductive inks and filaments. The issue of tin whiskers and metal fibers is an interesting one. These whiskers can cause short circuits, but are generally a problem for solid, bulk metals rather than thin, flexible fibers. 3. Microcontrollers. Assigning each sensor block a unique address via a microcontroller is a smart approach. This is akin to the subatomic organization in the human nervous system, where each area of the skin is mapped to a specific region in the brain. This will allow for precise identification and location of tactile inputs. 4. Fiber optic cables. Using fiber optic cables for data transmission is an excellent idea. They can handle a large bandwidth of data, are immune to electromagnetic interference, and are also lightweight and flexible. This could indeed serve as your spinal cord equivalent, transmitting data from the sensor areas to the central processing unit or brainstem. In this setup, pre-processing of the data could be done both at the level of the microcontroller's filtering, amplification, and at the level of the brainstem feature extraction, integration with other sensory modalities. Further processing and interpretation of the tactile data could then be performed by your artificial brain. Your concept is a beautiful blend of biology and engineering, and it really showcases the potential of biomimicry in designing artificial sensory systems. As with any pioneering technology, it will undoubtedly face challenges in development, but with continued advances in material science, electronics, and data processing, it has the potential to become a reality.
And that's all she wrote so far. I think it's kind of amazing that an AI can think your concept is beautiful. So, pretty cool. I thought I'd share. Alright guys, have a good night. Or morning, whenever you're watching this.